Rebecca. Hi, Rebecca.
Hey,
How's it going?
it's going good. I was just reviewing your videos before this class, so
Oh,
I should
good.
have a better understanding.
That would be the first hit I've had on it today. All right, first hit I've had on it.
Oh yeah,
Yeah, the kids that don't attend these things don't view them,
huh?
so they're going to be rudely surprised come test time.
I'd say so.
Yeah, because the stuff we just went over is not easy to get. So
It gets a little weird, but if you follow it, it makes sense.
amazingly, it does. Amazingly, it does. It helps if you have the physics along with it, but
Yeah, I didn't, so
yeah, it's when I went through it the first time, I didn't have my physics class in high school was horrible. So I didn't really get into the physics until freshman, or I'm trying to sit here and think. Had to be sophomore year.
Hmm.
I'm sorry, I'm sitting here thinking. I had chemistry, calc, German, and English. Yeah, that was it. Yeah. Must have had it my sophomore year. I got rid of all my requirements other than chemistry by the end of my sophomore year. So I got to have fun my junior and senior year.
Wow, lucky you.
Well, I mean, it's just,
Right.
well, it's a matter of what you had to take humanities courses and you had to take like social sciences courses.
Mm-hmm.
And those things were the fun ones. Those are the easy ones. I mean, after chemistry, these things are kind of easy.
Yeah.
So my GPA shot up from like, I started off at I think I had a 2.7. And by the time I got out of there, I think I had it up to a 3.28.
Oh.
So I was happy with it by the time I left.
Mm-hmm.
And besides, teachers put you in a niche after a while. If you take enough, by the time you get to be a senior in chemistry, there may have been, maybe at West Virginia University, may have been 12 of us that graduated with chemistry degrees.
Really?
Yeah. So they kind of got to know you. And so you got put into a niche. We had like these 3 really smart people that got the A's. I was in one of those, I was one of the person that was almost an A, but not quite. So it's just the way it goes. Then we had the rest of our B's and our 3 C's. They like to make it a nice bell curve. Is this all I'm going to have tonight? Nope, apparently not. Joe's in. It's better turnout than my morning class. I had 4 people in the morning class. I've got 5 here, so woo-woo. We'll see how it goes. Are you guys okay with the gas laws?
Yeah.
You okay with them? Jackson, Jessica, Dylan,
Hey,
and
Professor,
yes.
I couldn't make it to the last lecture and I didn't see the video posted on the
It should be
links.
posted.
I didn't see it earlier when I tried to look through it. I took notes on it anyway from the book and from your PowerPoint.
That kind of freaks me because I thought for sure I copied them. It's not, I've already copied it, Jackson. I just may not have put it in the, I keep on uploading this same PowerPoint or the same WordPerfect. That would have been, I'm seeing the 29th is all I'm saying. So.
Yeah, and that one was on the 1st, correct?
I'm sorry?
And that lecture, the lecture that I missed was on the 1st, I think.
I only have one of these in here. I only have one of them. No, I've got. Jackson, it will be up there. I've got it recorded. I know I've got it recorded. I just must not have re-upped my WordPerfect doc or my Word document. And
Okay, that's all I know. Thank you.
let me just check on it for sure. If not, I got a whole bunch of recording to do tonight. Yep, it's here. It will be uploaded tonight, okay? Along with this one, all right?
All right, thank you.
Sorry about that.
Don't worry about it. I should be okay for this lecture. I might be a little slower, but
So how are we doing with this? We doing okay? We doing okay with this, guys? Once we get into the actual equations, the actual problems aren't that bad. But it's just a matter of getting through this other happy horse shit. Okay. Gotta find out where I need to be. And then I gotta be there. Okay, I had no problem finishing this earlier. All right, what I really want you to guys to basically understand, the way I want you to interpret this in the test. I'm going to give you two basic equations. I'm giving you total force is equal to number of molecules times mass times acceleration. And I'm giving you the pressure is equal to force divided by area. Okay? Those two equations. Are we good with that?
Yeah. So are we gonna have to solve for the other ones?
No, you got to use logic. You got to logically explain why Avogadro's law makes sense.
Okay, so that's
Alright.
gonna be one of the questions on the test.
Definitely will be one of the questions.
Gotcha.
Okay? Pressure is equal to force divided by area. When you think area, think volume. Okay? Because area is part of what the volume is. Okay? If you're doing like a cylinder and you're getting the area of the circle, all you got to do is multiply it by the length of the cylinder and you have the volume, right? If you have the length and the width, you have the area, multiply it by the height, you have the volume. So think, when we're talking area, think volume, okay? When we're talking N, the number of particles, for that, what you need to think of is you need to think of moles, because the more particles you have, the more moles you have. Make sense?
Yeah.
Then for the little a is acceleration. Now, I don't know whether you noticed it last time or not, but there was something called a Boltzmann distribution. And basically it related 1/2 mv squared to a constant times something else. And that something else happened to be the constant times temperature. It was temperature that way. So basically, what we're dealing with acceleration, the Boltzmann constant related force to acceleration. That makes sense to you. So when you're talking acceleration, you're talking temperature. Now, when we are dealing with Avogadro's law relates volume and it relates number, okay? Pressure stays constant. Acceleration stays constant, okay? So if the pressure is constant and the only things that are changing are the numbers of the particles and the area or the volume, then if it's equal, if number divided by area is equal to a constant, the pressure, then as the number goes up, doesn't the area also have to go up to equal the constant? Does that make sense to you?
Yeah, so you're just plugging in different values.
No, I'm logically applying the equation to something that we already know.
Okay.
We know that as you blow more air into that balloon, the volume increases, right, Rebecca?
Yeah.
I'm just proving logically through equations how this comes to be.
Okay.
Pressure is a constant. That is what we're given in this particular problem. Pressure is a constant. Acceleration is a constant, so I'm not going to worry about the acceleration because it's a constant. If you want to, you can divide the pressure by the acceleration, and it's a constant divided by a constant that gives you a constant.
Okay.
Is that making sense to you?
Yeah.
So if I have a constant is equal to number of particles divided by my area. As my number of particles goes up, as my moles go up, doesn't my area also have to go up to equal a constant?
Yeah.
As the number goes down, the area has to go down.
Okay.
That's all I'm asking you to logically explain when we're dealing with the kinetic molecular theory. Okay? Now, think of it this way when we're trying to explain these things. There are three ways the force of a gas can increase the pressure. If I increase the temperature, acceleration goes up, force goes up, the pressure goes up. If I decrease the volume between the walls, don't I get more hits? If I have a volume this big and I got these gas molecules bouncing across, right? If I double the volume, don't I get half as many hits? And remember, pressure is the hits. They're going against the side of the volume. So as I increase the volume, am I not getting less hits? If I'm not getting less if I am getting less hits, this means my pressure is going down. Same thing with the number of molecules. If I have fewer molecules, I'm getting fewer hits against the side. Fewer hits against the side means that I've got less pressure. So bottom line for Avogadro's law, the more volume or the more moles you put into something, the bigger the volume is going to get. You take moles away, you're going to decrease the volume. That's all we're talking about with Avogadro's law. Okay, so we're going to get to a problem. All right, I need to point out this slide. The main obstacle we're dealing with when we're dealing with gas law problems are keeping the conditions straight. For this particular problem, I mean, which volume goes with which moles. That's the main problem. And professors will try and screw you up by wording the problems in different manners. I'm going to try and keep it straightforward, guys. Just be aware that other professors do that. And the main problem is keeping the conditions with one another. Which volume goes with which moles. Okay, new problem here. I got 12.2 liter sample containing half a mole of oxygen at a pressure of 1 atmosphere and 25 degrees Celsius. I convert all the O2 to ozone, O3, at the same temperature and pressure. What will be the volume of my ozone that I have formed? Do I have the first conditions? Jessica, do I have the first conditions?
Yes.
What are they?
The 12.2 liters
And
the 0.50 moles.
we got the first conditions, okay? Do we have anything about the ozone? Anything at all?
It just says the volume will be formed.
Do I have anything at all, Jessica? What am I circling here? Do you see what is this?
The 3 oxygens and the
It's a chemical equation, right?
Yes.
Is it balanced?
Yes.
So do we have a relationship between moles of oxygen and moles of ozone?
What do you mean by relationship?
Do we have a molar relationship between the oxygen and the
yes.
ozone? So do we know how much ozone or oxygen we started with?
Yes.
Can we determine how much ozone we made?
Yes.
So that's what we're going to do to solve this problem. If we have 0.5 moles of oxygen to begin with, and we have a 2 to 3 molar ratio, this means we have 0.33 moles of ozone. So from there, it just becomes a matter of substituting it into the equation. I got 12.5 liters divided by 0.5 moles. How many liters am I going to have with 0.33? I do that math out, I get 8.05 liters. Are we good, guys? We good?
Yes.
Okay. Now we're going on to our second law, our second individual gas law, Boyle's law. The volume of a gas is indirectly proportional to its pressure. In other words, as the volume goes up, pressure goes down. As the volume goes down, pressure goes up. An example of this, when you squeeze a balloon, doesn't it push back harder? If you squeeze it down real small, isn't the pressure inside that balloon trying to push out at you harder than it was when it was like this big?
Yeah.
Now, if you're going to look at this graphically, and I'm going to go into the slideshow because I got red on red. Why I did this, I'll never tell you. But can you see how the graph is curving? If I have a straight line and if I plotted something and I get a straight line, that means I have a direct relationship between the y-axis and the x-axis. If I get a curved line here, what that means is that I have an indirect relationship. Direct relationships mean as one thing goes up, the other thing will go up. An indirect relationship means as one thing goes up, the other thing goes down. All right. Boyle's law, we're relating pressure and we are relating volume. Temperature and moles stay constant. So do you remember my two equations? Pressure is equal to NMA divided by area, or force is equal to the sum of my two equations is pressure is equal to NMA divided by area. So if my N and my A are not changing, my mass of my particle isn't changing, my force, my NMA portion is not changing. So I've got my pressure related to 1 over area. As I increase my area, as I increase my volume, am I not dividing by a bigger number? I need an amen here, guys.
Yeah.
If I divide by a bigger, my area goes up, I'm dividing by a bigger number. If I divide by a bigger number, what does that make my overall number? Bigger or smaller?
Smaller.
So as my area goes up, as my volume goes up, I'm increasing the denominator. I am decreasing the pressure. Vice versa. If I decrease the volume, I'm dividing by a smaller number. If I am dividing by a smaller number, my pressure is going to go up. Another way to look at this, if my force is the same and my volume increases, then my distance between the surfaces increases. If my distance increases, I get less surface hits per time. If I get less hits per time, this means that my pressure is going to go down. If force is the same and I decrease the volume, I got a smaller distance between my two walls. I'm going to get more hits. If I get more hits, pressure goes up. Ultimately, this is Boyle's law. P1 V1 equals P2 V2. At a constant temperature in moles, if you multiply the pressure times the volume, you get a constant. So if you change either the pressure or the volume, you're going to change the other one automatically. But it's still going to be equal to that constant. So my P1 V1 is equal to K, which is equal to P2 V2, or P1 V1 equals P2 V2. If you want to think about it along the original ideal gas law that I showed you, if you want to think about it along that original ideal, stop that. Oh, I know why. Then what we're going to do is we're going to have P1 V1. Why aren't you doing anything to me? P1 V1 P1, there we go, times V1 divided by N1 T1 is equal to P2 V2 divided by N2 T2. Now remember, we said moles and temperature are constant. So if moles and temperature are constant, eliminate them from the equation, and you get P1 V1 equals P2 V2. Are we good with this stuff so far? Boyle's law, we're halfway through them. We good with them?
Yeah.
Okay. When the spark plug ignites a gasoline in a car, the piston has a pressure of 6.45 atmospheres and a volume of 135. What happens is the pressure forces the piston out. And when the piston reaches its maximum volume, it's 426 centimeters cubed. What is the pressure at that point? David, do I have a set of parameters here?
Yeah, you've got the initial volume and pressure, and you have the second volume.
So set up the problem for me.
So it would be 6.25 times 135 equals 426. So you would multiply those out and then divide it by the 426 to get the volume, or the atmospheric pressure.
Okay. All right. Now, when it was combusted, have I created any more molecules? Have I added any more than when the gasoline first got ignited?
No.
So the moles are staying constant. Down here, I'm telling you the temperature doesn't vary. Those two constants get thrown out of the equation, and as David said, I'm going to take my 6.45 atmospheres times 135. That's equal to P2 times 426. Notice, guys, I didn't bother to change the labels. Why didn't I bother changing the labels?
Because they were the same on both sides.
And they're going to cancel out. If I wanted to change this to liters, I'd multiply this by 1 liter over 1,000. I'd have to do that on the same other side of the equal sign. So they're going to cancel out. But just know that whatever you're solving for is going to have the same label as the opposite side. A 1.5 sample of gaseous freon at a pressure of 56 torr is increased in pressure to 150 torr at constant temperature. Let me get somebody else up here. Cassidy.
Yes.
1.5 liter sample that's at a pressure of 56 torr is increased in pressure to 150 torr. Did my volume go up or go down?
It went down.
Went down because they're inversely related. Pressure went up, volume has to go down. Now, Cassidy, do you feel comfortable enough to figure out what the volume is on that?
Yeah, because you would just multiply the 1.5 liters times the 56 torr and then divide by that by the 150 torr, and then that would give you your volume.
Which is 0.56 liters. Are we good, guys?
Yeah.
Are we good with this?
Yeah.
Do I need to go through another problem?
Not at all.
Thank you so much, because if I keep on going through these problems, they get very, very boring after a while. Okay? Third law. In the third law, we're relating temperature to volume. It's directly proportional to the volume. As the temperature goes up, volume goes up. Temperature goes down, volume is going to go down. The example of this, has anybody ever seen them? Actually, it's fascinating. I lived in California. I saw this a couple times. They used to have hot air balloons that would float over Napa Valley. When the air balloon starts out, it's flaccid. It's just lying on the ground. But as they heat their propane lighter up, they actually are able to heat the air molecules that inflates the balloon. As I said, if I were to do this graphically, I would find that I had a straight line because they are proportional. As one goes up, the other goes up. Now, remember our two equations. Pressure is equal to force divided by surface area. Force is equal to number of particles times mass times acceleration. Now, when I'm dealing with Charles' law, pressure is constant and the number of moles is constant. I'm relating temperature with volume. Temperature is a measure of how fast things are going. It is related to acceleration. So the faster the molecules move, the higher the temperature has to be. Now, if I have this equation and I combine the two, okay. The two things I'm thinking about right now are acceleration that I can relate to temperature and area that I can relate to volume. My number is constant and my mass is constant. So if I divide my number and mass by my pressure, I'm still going to get a constant. So if my acceleration goes up, if my temperature goes up, in order for my equation to be equal to a constant, as my acceleration goes up, as my temperature goes up, my area or my volume has to always go up. All right, basically what happens? Why do we know that the pressure, how do we know the pressure inside the balloon is the same as the pressure outside? Have I stumped you? Why do we know the pressure inside the balloon is the same as the pressure outside?
Because it's deflated.
Nope.
I don't know.
Is it getting any bigger?
No.
No.
No, it's not.
Balloon
Well-
keeps on getting bigger until the pressure inside equals the pressure outside. That's how we know that the pressure is constant. Okay, now, If we're dealing with different gases, they react differently. In other words, the slope of my direct line is different for each gas. Why would that be?
Different molecular weights.
Could be. Remember, it is related. Force is related to the mass. Okay? Not really true, because there are other things that are taken into account, because the hydrogen reacts at a lower rate than water or methane. So there's something else going on, and this has to do with the fact that when we set this whole thing up to begin with, we were talking about ideal conditions, okay? Because we were dealing with ideal conditions, that meant there was no interaction between the two molecules. So mass does have a part to it, but there's also this interaction that goes on. So when we're using Charles' law, pressure in moles must be constant. So in that case, we get V1 over T1 is equal to a constant that equals V2 over T2. And I can just remove the constant, and I have V1 T1 equals V2 T2. Anybody see a problem with T's being on the bottom side of a fraction? Anything, guys? Any problem with that?
Is it because that temperature could be 0?
You have to put the temperature in Kelvin. This is the only one of these problems that you have to worry about that. If you have temperature, you need to put it into Kelvin. All right, so basically what you're going to do is change Fahrenheit to centigrade. And once you have centigrade, then you add 273.15 to it. Guys, I need to take my leave of you for a second. So what I'm going to do is I'm going to give you one of the tough problems. Not that one. Crap. I got a series of problems here, guys. Give me 5 minutes or so, and I'll be right back, okay? Please do the problems. I'll be right back. Okay, I'm back. Anybody out there?
Yeah.
Okay. I haven't done Dalton's law of partial pressure, but did you guys remember it?
Not exactly.
Not exactly.
No.
Okay. Do you notice something about the first problem?
Yeah, it says over water. right?
Okay. When it's collected over water, that means you have to deal with the water vapor pressure. And that means that the total pressure, the pressure that is listed as 770.4, you have to subtract the water vapor pressure from that to get the pressure of the gas itself. Okay? Did you
Yeah.
notice anything else?
It also
Are-
says partial pressure.
What's that?
Partial pressure?
Okay, yeah, that's,
Well, I noticed that the two temperatures are the same that they're giving us.
okay. Are any of the conditions changing?
The pressure is.
No, pressure's not changing. The total pressure is going to be equal to the pressure of the H2 plus the pressure of the water. But the pressure of the water and the pressure of the H2 are not going to change. Are any of the parameters changing? I'm a little bit ahead of myself, I realize that. Are any of the parameters, is the volume changing?
No.
Okay. If I tell you that the total pressure is 770.4 and the water pressure is 25.2, therefore, if I subtract the two, I get 745.2. That's the pressure of the hydrogen. Is the pressure of the hydrogen changing?
No.
No.
Is the temperature changing?
No.
When conditions don't change, use the ideal gas law. PV equals nRT. So basically, what this first problem comes down to is changing the 745, and I'll get into this, and I'll get into this when I get into Dalton's law. But 770 minus 770.4 minus 25.2 gives me 745.2. That's millimeters of mercury. I have to change that into atmospheres. I have to change my milliliters into liters. So I changed my pressure in atmospheres, multiply that by my volume in liters. That's going to equal N, what I'm trying to find out, times R 0.08206 times the 23.3 changed to Kelvin. Sorry, I'm sorry, I quickly had to get out of here for a second. So we are going to get into that.
I'm sorry, Professor. When it asks for partial pressure, is that what we have to do? Is we have to subtract the initial pressure from what they give us?
Yes.
Okay.
Yes. Yes. Especially if you hear of something being collected over water, especially in Florida, because of the heat here, water exerts some gaseous pressure. We call that humidity. So there is some water vapor in the air. Because there's water vapor in the air, it adds to the total pressure. So you have to add the water vapor pressure plus the pressure of the gas you're interested in. Both of those together will equal the total pressure.
So over water and partial pressure are talking about the same thing.
Yes. Yes. Okay, getting back to Charles' law. And I think I was right about here. Okay. Now, when we're dealing with Kelvin, we're dealing with something, we're dealing with the temperature being related to absolute zero. Remember, we define temperature as being the kinetic energy of the substance. Absolute zero is defined as that temperature when all molecules cease movement. So since the molecule still has mass at absolute zero temperature, it's related to the velocity. And the value of the temperature when all movement stops is equal to negative 273.15. So all we're going to have to do is take our degrees Celsius and multiply it by 273.15. Guys, do yourselves a favor. Most thermometers are measured out in degrees, which means you can estimate them to the 10th of a degree. Do yourself a favor when you're converting to Kelvin. If your temperature goes out to the tenths, add 273.2. If your temperature just goes out to an even number, no decimal point, then you can add 273. The reason I tell you 273.2 is because, look, whatever number this turns out to be, if I'm adding a degrees that goes out to the tenths, my answer is going to be reported out to the tenths. I look over to the right, I see a 5. That means I'm going to automatically up at 1. So when you're adding this, add 273.2. Min, you out there, Min? Min? Blake,
Hey, what's up?
you got 2.5 liter sample of nitrogen. It's collected at 273 and heated to 325. Calculate the volume of the nitrogen gas. Assume constant pressure in moles. First question, does the volume go up or down? Temperature's going from 273 and it's ending up at 325. Volume go up or down?
It'd go up.
Goes up because it's a direct proportion. Now, set up the equation for me.
2.5 liter over 273 Kelvin equals 325 Kelvin. You divide.
Nope, be careful what you're doing. What you told me was 2.5 divided by 273.
Mm-hmm.
That's
Is that
equal,
wrong?
that's equal to what?
Oh, yeah, you're unknown. So it'd be an
X?
X. Yeah, over 325K.
Yes, that's what I'm telling you. You got to be careful when you're setting these problems up to keep things
Yeah, I
where they're
skipped
supposed to
that.
be, because there are stupid mistakes that get made. You do that math out and you end up with 2.9 liters. Indeed, this is another way you can check. First off, you looked at the equation, Blake, you said, okay, the volume has to go up. Did the volume go up?
It did.
So therefore, you probably have the right answer in.
Cool.
Joe, please set this problem up for me. I got 87.2 liters that was collected at 285. What is the temperature if the volume is reduced to 75.0? Does the temperature go up or down, Joe?
It goes down.
Goes down because the volume went down. So set it up for me, Joe.
So your volume 1 is 87.2 liters, and then your temperature 1 is 285 K Kelvin, and then you have the liter 2, so you're trying to find volume 2.
No, you're not trying to find volume.
Temperature 2. Temperature 2.
So where
So
you got 87.2 over 285 is equal to
75
over
0
X.
liters.
You do that math out, you get 245. Okay? Last law. This is the Casey-Jones law. Guy-Lussac's. Temperature is directly proportional to pressure. In other words, as temperature goes up, so does the pressure. As temperature goes down, so does the pressure. Think of a locomotive engine. If you want the locomotive to go faster and faster, you need more pressure. To get more pressure, you put more fuel into the fire, get the temperature of the steam going, getting really, really hot. Again, pressure is equal to NMA divided by surface area. Surface area stays the same. Number of particles stays the same. So the force is directly related to the acceleration. As you increase the temperature, acceleration goes up, force goes up, pressure must go up as well. Guy-Lussac's law, P1 over T1 equals a constant, which is equal to P2 over T2. Or P1 over T1 equals P2 over T2. Are we good with these guys? Do I need to go through some more problems?
No.
You said that real quick, Rebecca. Seriously, guys, you think you're pretty good with these?
I'm good with this kind of stuff too.
We good, guys? All right. I'm going to skip over. I'm going to get to the combined gas law. Sometimes when you're dealing with the problem, you can change every one of the parameters can be changing. So you have P1 V1 over N1 T1 equals P2 V2 over N2 T2. Sometimes you get a problem where the moles are constant. In that case, you have P1 V1 over T1 equals P2 V2 over T2. New conditions and old conditions must equal the same constant. Okay? Combined gas law problem. A mass of argon occupies 5 liters under a pressure of 740 millimeters mercury on Miami Beach at 30 C. What volume would that argon occupy if it were on Mars? Surface pressure on Mars is about 0.6% of Earth's pressure, and the temperature is 20 C. First question I have for you. Extra credit point. The first person that answers the question, does the volume increase or decrease?
Decrease,
Why?
because the temperature decreased.
But what about the pressure?
It's less.
So pressure going down, that increases the volume, right?
It does.
Okay. On the other hand, temperature going down decreases the volume. Do I have conflicting things going on here?
You do, yeah. You tricked me.
Yes, I did. So if you have conflicting things can you tell just from the problem, just by reading the problem, can you tell whether the volume increases or decreases?
No.
On the other hand, if I gave you another problem that said that the pressure went from 500 torr to 760 torr and the pressure went from 760 torr to 500 torr and the temperature increased from 35 to 45 degrees Celsius. Am I in conflict there? My pressure went down. My pressure went down. That means my volume goes up, right?
Right.
My temperature increased, which means my volume must increase.
Right.
So under those circumstances, with the pressure going down and the temperature increasing, I can confidently say that my volume will increase. Make sense?
Yeah.
You got to sit there and analyze the problem that's being asked.
But we would have to use the combined gas law, the P1 V1 over T1 equals P2 V2 over T2 to solve that kind of problem, right?
Yes. In this particular instance, what you would have to do is you'd have to figure out what 0.6% of 740 is. And I think that's 4.44. I did the problem earlier. So what it's saying is if the pressure on Earth is 740, it's going to be 4.44 millimeters mercury on Mars. The temperature on Miami Beach is 30, which means 303 K. On Mars, it is 293 K. The volume is 5 liters on Earth. We don't know what it is on Mars. So to set that problem up, I would do 740 times the 5 liters divided by the temperature, 303, is equal to the pressure on Mars times the new volume that we don't know, divided by 293. I do this math out, I get an answer of 805. Questions, guys? Sorry, questions? All right, now let's talk strategies, okay? We also have one more law that I alluded to at the very beginning. I derived the ideal gas law, if you remember it correctly, right? Right?
Yeah.
All right, strategy. Look the problem over. If nothing is changing, use the ideal gas law. If something changes, then keep whatever's changing, get rid of whatever is staying constant. Using the equation P1 V1 over N1 T1 equal P2 V2 over N2 T2. Get rid of what's constant, keep what is changing. Then solve for it that way. So that's why you know when you're using the ideal gas law. This problem, Min, are you out there, Min?
Yeah, I'm here.
Okay, Min, look at the problem I have on the screen here for you. Is the pressure changing, Min? Do I give you 2 pressures, Min?
I see just one pressure.
One pressure, it's not changing. How about the volume, Min? Is it changing? How many volumes do you see there?
I see one.
One volume. How about temperature? Temperature?
Temperature 1.
1. I'm only seeing one of pressure, volume, and temperature. This means nothing is changing. I use the ideal gas law. And most of the time, ideal gas laws are doing nothing but making you change from one unit to the other, because the key to an ideal gas law is the constant R has a label, liter atmospheres per degree Kelvin mole. So pressure has to be in atmospheres, volume has to be in liters, temperature has to be in Kelvin.
Okay, I got it. So
I have,
we can,
sorry, Min?
so we change the temperature 0 Celsius to Kelvin.
To 273, yep.
273 Kelvin.
So I have to change to 0 degrees Celsius to 273, and I'm going to plug it into this equation. In this case, I rearranged it a little bit, and I got PV over RT is equal to N, 1.5 atmospheres times 8.56 liters divided by 0.08206 divided by 273. My N is equal to 0.57 moles. No, $1 million question, Cassidy.
Yes.
Are these moles any different from the moles you get when you have grams and you divide by the molecular weight?
No.
Are they different from the moles you get when you have the volume and you have the molarity of a
No.
solution? Moles are moles, guys. So I can take these moles, plug it into a stoichiometric equation. What volume is occupied by 11 grams of carbon dioxide, 25 degrees Celsius, 371 torr? Dylan, haven't bothered you yet today, Dylan. Dylan, are my conditions changing?
No.
So, do I have a way to get moles?
Yes.
I have the name of the compound and I have the fact it's 11 grams. So I can divide the 11 grams by the molecular weight of the carbon dioxide to get the moles. Dylan, can I convert to Celsius?
Yes, just add 273.15.
So I get 298 there. Okay. My torr, can I convert that to atmospheres?
Yep, divide by 760.
And I do that math out and I get, yeah, I didn't do the equation. Okay, this is equal to 0.25 times 0.082 times 298 divided by, 371 divided by 760 is equal to 0.488. I do that math out. And I end up with 12.5 liters. Questions about this, guys? Okay. Methane gas is kept in a tank that has a volume of 5 liters at minus 32 Celsius and 6.2 atmospheres. It's released in a room with 1.05 atmosphere pressures at 25 Celsius. What's its new volume? David.
Yeah, I'm here.
Are my conditions changing?
Yeah, you have a difference in pressure and a difference in temperature.
Okay, and a different, what's implied?
The volume.
Volume's changing. Have I mentioned moles?
No.
If I haven't mentioned moles, assume that it's staying constant. If you have a question, give me a call on the test, okay? But if it's not mentioned, assume that it is constant. So David, how am I going to solve this problem?
Okay, so you'd have, So you have the pressure, the volume. Would you do the P1 V1 equals T1, or I'm sorry, P1 V1 over T1 equals P2 V2 over T2?
Exactly. And you do that math out, you get a volume of 37.9.
Perfect.
Okay. I got a sample Just tell me. Just tell me how you'd solve this one. We've got 10 more minutes to go here. And I want to get into Dalton's law in the next couple seconds. Joe, are conditions changing in this problem, Joe?
Yes.
So which law am I going to use? Is the
When you need to
temperature
find
changing?
temperature,
I'm sorry,
but you need to find the new temperature, so the temperature's not changing.
but it's not changing. What's implied, Joe?
Negative 15 Celsius.
That's
So
what
it's
it
not-
was originally.
Yeah.
What's it by the question? What's implied?
I get what you're saying about that. I get what you're saying.
Okay, by saying what will the new temperature be? Isn't it implying that the
Yeah, we can
temperature is
find-
changing? Okay, so the
different one.
temperature's changing. Is the pressure changing?
Yeah.
And the volume?
Yeah.
And the moles are staying the same. What law am I going to use?
The same one we just used, P times V divided by 2. I mean,
Okay. Now, last law, last gas law is something called Dalton's law of partial pressure. And all you need to know about this is the total pressure of a mixture of gases is equal to the sum of each individual pressures of the individual gases. So if you have 3 gases, the total pressure is going to be the pressure of gas A plus the pressure of gas B plus the pressure of gas C. Now, again, as I mentioned earlier, if you collect a gas over water, there will be a pressure that is added to the pressure. There will be a pressure contribution from water to that entire pressure inside the bubble. I can't. I'm frustrated because I can't draw something right now. And why is that? There we go. I'm sorry, I'm trying to look for something more. Nope. We're going to try this. Okay, you see this little mark here? You can see my drawing abilities are somewhat limited. Okay. Now, what we are talking about, we have this tube, and the tube is in a water bath, and we're using another tube to bubble gas up through here. A lot of the chemical reactions do this. So we have little bubbles up here that are coming up, little bubbles, okay? And making the hydrogen gas in there. Now, the gas pressure takes this downward until it equals the pressure of the atmospheric. Does that make sense to you guys? The pressure of the reaction gas keeps on pushing this downward until the pressure inside here is equal to the pressure pushing down on the water. Does that make sense to you? It's the same principle as a straw. The reason a straw works is you suck all the air out of the straw, that creates a vacuum, so the pressure that's pushing down on the soda pushes it up the straw. Does that make sense to you?
Yeah.
All right. Now, we can measure the atmospheric pressure out here. We can just take a barometer in the room. Okay? We can measure the water vapor temperature because there are charts which will relate the temperature of the atmosphere with the water vapor temperature. If the temperature is 25, this gives me this many torr of water vapor pressure. So in that instance, to get the pressure of the gas we're collecting plus the pressure of the water vapor equals the total pressure. Does that make sense to you?
Yes.
So in order to get the pressure of the gas, we have to subtract the water vapor pressure from the total pressure. Now I can hopefully, boom.
So will we need a chart for
No,
the water?
normally you would, but I will give you that answer.
Okay, all right, thank you.
I'm trying to find the problem I need. A gas occupies 730 milliliters at 65 degrees Celsius and 830 torr when it's collected over water. What volume does it have at STP? Vapor pressure of water at 65 degrees Celsius is 187.5 millimeters mercury. I have the volume of the gas, do I not, ladies and gentlemen? I have
Yes.
the temperature the gas is under. Okay? I have the pressure. What volume does it have at STP? Are my conditions changing?
Yeah.
Did everybody catch that? Why is it changing? Who answered that?
I did, David.
David, why are they changing?
Well, because you're changing it to standard time and pressure or temperature pressure.
So it's no longer at 65 degrees Celsius. It's now at 0 degrees Celsius. It's no longer at 832 torr. It is at 760 torr. Okay? But we got to do one thing though before we can do this.
Subtract the 832 from the 187.5. Or
You got to do
vice
that.
versa, but yes.
Right? Exactly right, David. I got to subtract my water vapor pressure from my total pressure to get the pressure of the gas. Then I simply multiply that in. So in this instance, I would get 832 minus 187.5. That's 644.5. So if I'm doing this, my pressure is 644.5 times my volume, which was 730 milliliters, divided by my temperature, which is 65. Which is 338. This is equal to 760 times X divided by 273. I do that math out, I'll solve for X. Do we feel fairly confident with this, guys? Are we okay with it?
Yeah.
Now, as I mentioned before, the moles you get from the ideal gas law are the same moles as moles created from grams divided by molecular weight or milliliter or liters multiplied by the molarity. All moles are moles. So what mass in grams of sodium oxide is necessary to consume 1 liter of CO2 at STP? Do I have a way of getting moles of CO2?
Yes.
How do I do that?
You divide by 22.4 and then multiply by the molecular weight.
Good choice. You can, yes, absolutely. You can do that. You can take the 1 liter and divide it by 22.414. That will get you moles. You can also do it by using the ideal gas law. And in either case, the answer you would get is 0.04461 moles. Then we use the molar ratio, just like we did before, and then multiply it by the molecular weight of the Na2O2. Do I have any questions, guys? Are we okay? Do we have a good idea how to solve gas law problems?
Yep.
Yeah.
Guys, any questions? If there's no questions? No questions?
One question.
here.
So why is the R at a constant 0 point, what was it again?
0.08206?
Yeah.
Why?
Mm-hmm.
Okay, because of the other day. Do you remember when we actually derived the equation?
Yeah.
Way back when? One of the last things we talked about. Okay. Okay. At one point, Rebecca, we derived this to the point where we got to PV is equal to NKT. Do you remember that?
Mm-hmm.
All right. There is a conversion from N to get to moles. Okay?
Mm-hmm.
And when you go from N to get to moles, that gets incorporated with the constant K.
Okay.
And you multiply those two constants together, and what you end up with is R.
Oh, okay.
Now, you have to remember, R will change. If the label of R changes, the number changes.
Mm-hmm.
Next semester, you're going to be dealing with joules per K, km, I believe. And so at that point, it's no longer 0.08206. At that point, it's 8.31.
Oh,
If you
okay.
change the label of R, you change the number.
Mm-hmm.
Okay?
Yeah.
Anything else, guys?
I'd
Okay,
like to talk to you after class.
okay, no problem. I'll be here. Okay, guys, if that's it, then I will see you. I will see some of you at 7:30. I will see some of you at 7:30. Unfortunately, it takes that long to upload this thing into the recording. Others of you, I will see next Tuesday. Remember, test on Thursday. Test on Thursday will cover stoichiometry It will cover solution. It will cover acids and bases, and it will cover the gas laws. I've already given you an indication of what the one question is. About a tenth of your question, about a tenth of your points will involve the kinetic molecular theory of gases. There will be 8 problems and 9 true-false questions that are going to involve properties of acids and the solution definitions. There is a practice test up.
Professor, with the practice test, is it like an unlimited amount of tries?
The practice test?
Yeah.
Yeah.
It's a Word document.
Oh,
Thank
okay.
you. Thank you. Thank you very much. Yeah, it's not like it's on a quizzes. No, it is, you look on the modules. In the modules, I think there is a module labeled practice test or something like that. Inside of that, you will find a practice test too. And there are answers. I did check them, but I'm a lousy editor, guys. So I think the answers are correct. 95% sure.
And you want us to email you again about accessibility?
Yes, you mean for extra time?
Yeah.
Please.
Okay.
Anything else, guys? That's all I got for you. And I think it was Cassidy that wanted to talk to me after class.
Jessica.
Jessica, sorry. Okay. Guys, I need you to
Bye.
get off because it's a private conversation, okay? If anybody has any questions, please ask. Min?
No.
Please get off. Min, thank you very much. Jessica, what's going on?
Could we stop recording right now?
Okay. Maybe I gotta find the silly thing. Oh, it's up there. Okay. Nope, stop share, okay. I'm sorry, Jessica. I'm gonna stop the video. Pause, stop recording.